What's up, guys? Welcome back to the 12 ISLs of Christmas. Today, we're going to be discussing the finale to the series, a nice geometry problem from the 2021 shortlist. This is 2021 G4. And the problem is, let ABCD be a quadrilateral inscribed in a circle omega. Let the tangent to omega at D meet rays BA and BC at points E and F, respectively. A point T is chosen inside ABC so that TE is parallel to CD and TF is parallel to AD. Let K be a point on segment DF satisfying TD equals TK. And you wish to prove that these three dashed lines are concurrent. Alright, so how can we get started on this problem? Well, if we want to prove that three dashed lines are concurrent, it might help to define the intersection of two of them and prove that that lies on the third line. So we can just let this intersection of BK and DT be some point, suppose Z, and you want to prove that Z lies on AC. So it may help to look at lines BD and TK, or something like that. So if we look at this and this, it looks like they're parallel. And let's prove why they should be parallel. And again, this is a G4, so it shouldn't be that obvious immediately. But suppose that they were parallel. Then if they were parallel, then this motivates us to think about homotheties. Because if we look at Z, if that's the intersection of BK and DT, then that means that Z sends a homothety from BD to KT. So if we prove that it sends a point on AC to another point on AC, then we're set. And let's see where it sends A to. Well, we know that AD is parallel to T, the line connecting T in the image. So that means that the image should be somewhere right here. So let's call this point Y. So it seems like this point Y will definitely be useful to us. And similarly, this point X as well. But again, we don't really know much information, so we should go ahead and go backwards. We need to erase these segments BD and TK and forget that point Z existed. Although it seems like the points X and Y will be useful, as I said earlier, because recall that A should be sent to Y and C should be sent to X. Alright, so now we have our points X and Y. And our next goal is to look at some relations involving the points X and Y. If you're good at spotting cyclic quadrilaterals, I'll go ahead and give you guys a minute to look for cyclic quadrilaterals in these pictures. Feel free to pause the video and see if you can identify three different cyclic quadrilaterals on your own. All right, so let's go ahead and see what we find. So one cyclic quadrilateral that you might spot is AEDX, and by symmetry, FCYD. So let's go ahead and draw those in. But before we draw those in, we need to prove that they're cyclic, actually. So in order to prove that they're cyclic, we want to show something like directed angle AXE is equal to directed angle ADE. And we're comparing these two specifically because we know a lot about angle AXC because it's right at the intersection of the lines. So let's see what we can do here. We know that ET is parallel to DC by the problem condition. So that means that directed angle AXE is equal to directed angle ACD because XE is parallel to CD and we just shift this over. And this one here, we want to prove that it's equal to angle ACD. Now, angle ADE is negative angle EDA, and EDA inscribes a tangent because ED is tangent. So that means that this is negative angle DCA, and that's just ACD. And this proves that the quadrilateral is indeed cyclic. All right, so now we know how to add x into the picture. So let's go ahead and draw in these circles. So we have that one there, and by symmetry, we have this one here. Sorry if that's off the screen. But wait a second. It seems like they're tangent at point D, and that TD is a tangent. This could mean a lot to us, because if they're indeed tangent, then we already know how to introduce point line TD in the problem. So let's see how to prove they're tangent. So if we prove that TD is tangent to this circle, then we're set. So we want to prove that angle TD and some point M is equal to directed angle D some point N and some point M, where M and N are points on the circle to be chosen. So what could be good options? Well, we don't really know a lot about the line TD still, so angle TDA and angle TDE might not work yet, and it seems like we might go backwards. So this leaves us with only angle TDX. And when we look at TDX, we want to show that's equal to D something X. And angle DAX is very approachable because that's just DAC. So we just need to show that angle TDX is equal to angle DAC. But if we work backwards from proving that these circles are cyclic, we know that this here is equal to directed angle FDC, which we know is directed angle FYC. And we're getting really close to the area of TD and X. So if we rewrite angle FYC, this is just directed angle TYX. So we need to prove that angle TDX is equal to angle TYX. In other words, we must prove, we already proved this, we need to prove that TXDY is cyclic. And fortunately, this is not super hard because we were comparing these angles here. And instead, we can just compare these angles here because we know a lot about those. And indeed, we have directed angle TXD is equal to directed angle EXD is equal to directed angle EAD, which is directed angle BAD, which is directed angle BCD, since we're now using the fact that the quadrilateral is cyclic, basically. And then we're just going backwards from here, because then this is just directed angle FCD, which is directed angle FYD, which is directed angle TYD. And this proves that the quadrilateral is cyclic, and therefore that these two circles are tangent to line TD. Okay, so we know that TD is tangent to both of these circles, but we also got a bonus piece of information out of this, that TXDY is cyclic. So let's go ahead and draw in the circle. So we have something like that, and then we go this way a bit, and wait a second, it passes through K. So we want to set our sights on proving that this circle passes through K. But now there's a piece of information we didn't use about K, that TD equals TK. So let's see how we can use this. So first we have directed angle TKD, and we're looking at TKD because we want to compare the base angles. That is equal to directed angle KDT, because the base angles are equal, which is directed angle EDT, because K lies on EF. So we've incorporated both of these pieces of information. But now we recognize that this here that TD is a tangent, and we want to use this somehow. So ED is a chord in the circle, and TD is a tangent. So we can rewrite this as negative directed angle TDE. And now by the tangency, this is equal to negative directed angle, and we want to somehow choose either A or X to satisfy this. And when we have TKD and this circle here, it makes sense we want to prove that it's equal to TXD. And TXD is equal to EXD. So it makes sense to do angle TDE is equal to negative directed angle DXE, which is angle EXT, which is angle TXT. And therefore, this proves that K lies on the circle. So that means that we can indeed draw this circle in here. At this point, we have lots of information, including one that directly involves the point K. And at this point, we can find even more information. So, for example, if you may have noticed this from earlier, but E, X, Y, and F are concyclic as well. And we actually don't need to prove that in this problem. And you could prove it because it's not a very hard to prove. It's just this very simple angle chase. But we need to keep our eyes on the prize. And in this case, recall from what I said at the beginning of this video, we want to prove that somehow that BD is parallel to TK. So we want to find some base angle for each of these guys, and line EF seems to do the trick. Because K lies on EF, KT has a good relation with EF because of the circle, and we also know about EDB because of the tangency. So we wish to prove that directed angle EDB is equal to directed angle EKT. Now, directed angle EDB by the tangency, that's pretty easy to conquer. That's just DAB. Now, directed angle EKT, that's just directed angle DKT. But recall how directed angle DKT, because of the circle, is directed angle DXT. And this is directed angle DXT. And this is directed angle DAE by the circle here. And that means that this is just directed angle DAB. So that means that these two angles are equal, and therefore the two red lines are parallel, as we need. And now that we have this, we can actually consider the center of homothency, sending B to K and D to T. And we hope that this lies on AC. And recall how I said from earlier that we want A to be sent to Y. So if we show that ABD is sent to YKT, then we are set, because then AY, which is AC, BK, and DT are concurrent, as we need. So if we show that these guys are homothetic, meaning that there's a homothency sending one to the other, then because Z is the intersection of these guys, that intersection must be Z, and therefore that's the center of homothency. So we just need to prove that the homothency sending this one to this one exists. We already have one pair of parallel sides, and in order to show that a homothency exists, we need to show that there are three parallel sides. So we already have BD is parallel to KT. What about AD is parallel to TY? Well, that's already given, because recall from the problem statement that AD is parallel to TF, and Y lies on TF. So that's done. And BD, and also BD is parallel to KT is done. So all that's left for now is AB is parallel to YK. And when we prove this, we finish the problem. And again, we can use the base angle EF as a reference, because KY works well with EF. So anyways, we get directed angle FKY is equal to directed angle DKY, which is directed angle DXY. And we're just doing stuff at this point. And DXY is equal to directed angle DXA, which is directed angle DEA. And this here is just directed angle. We can just extend this all the way to F, and that's FEB. So FKY is FEB, and therefore AB and KY are parallel. So all of these guys are parallel, and therefore there's a homothency sending one to the other. And that homothency is the intersection of BK and DT, and that. So what's the main takeaway from this problem? Well, we found lots of information, and we use that to solve the problem. So that brings us to our first takeaway. Find as much information as possible. And in this case, by finding lots of information, specifically all of these cyclic quadrilaterals, or even pentagons on that matter, we were able to solve the problem. But we could have found more information easily, but we stopped ourselves because of the second takeaway, which is to keep our eyes on the prize. In this case, the prize is the problem. We want to focus on what we want to prove and look at what our original motivations were when solving the problem. In this case, our original motivation for constructing X and Y was wanting to prove that there's a homothency somehow. And then that meant proving BD is parallel to TK. And we wanted to not forget that. And we still prove that BD is parallel to TK. And that way we could solve the problem by considering more homotheneys. So thank you so much for watching this video, and thank you in general for watching this entire series. It was amazing to guide you guys through many different ISLs. And I hope you enjoyed the series, and I'll see you sometime soon. Bye-bye.